All right, I want to welcome everybody to the AOML HRD seminar series. Today we have the pleasure of Dr. Paul Layton presenting on raindrop size distributions in hurricanes. Hua joined HRD in 2014 as a postdoc from the University of Maryland, and then joined as a CMIS staff member, CMIS scientist in 2016. Hua has been working with the modeling group and in our microphysics efforts for the last few years now with Bob Black and myself and Zujin. And she's going to talk about some of her recent results looking at raindrop size distributions. Please mute your mics and close your cameras to allow the most bandwidth for Hua's presentation. We will suspend questions until the end of her talk. If you have any questions, you can enter them into the chat and we'll address them one at a time after she's done. So with that, Hua, it's all yours.
Okay, thanks, Frank. I'd like to thank my co-authors, Robert Black, Xueji, and Frank Marks. So first of all, what is raindrop size distribution, since we're studying the raindrop size distribution? So what we're looking at right now is a histogram. The horizontal axis is a drop size, and the y-axis is a number concentration. So basically, the raindrop size distribution tells us how many raindrops in each size bin. Then how can we measure the raindrop size distribution? Overall, there are two kinds of instruments, the ground-based, the surface disdrometers, and also their instruments, imaging probe that are mounted on the aircraft. And the PIP probe, precipitation imaging probe, that's the one that we use for this study. So the image we're looking at right now is a raw image from a PIP, and we use a software called SOJA2 from NCAR to generate this histogram. And these are the data sets we used for this study, and they're from 17 flights from 6 hurricanes in 2020. And overall, there are over 18,000 samples. And this figure shows an overview of this data. So it shows a histogram of altitude, wind speed, vertical motion, the liquid water content, radar reflectivity, rain rate, mass weighted diameter, and total number concentration. And the first three variables, altitude, wind speed, and vertical motion, are directly measured. And the liquid water content, radar reflectivity, rain rate, mass weighted diameter, and number concentration are calculated from the raindrop size distributions. So as we can see here, most of our observations are taking place near 3 kilometers. That's where our flight level is. And also the majority of our data are taken in a region where vertical motion is relatively weak. So as we can see, the majority of the vertical motion has magnitude less than 1 meter per second. So then why do we care about the raindrop size distribution? What are the applications of the observed RSD? So there are two applications. The early one, starting from 1950s, 1960s, people used the RSD to develop a ZR relation, which is Z stands for radar reflectivity and R stands for rainfall. So they developed such relationship so they can estimate a rainfall from radar reflectivity. Another application is that we can use the RSD from the observation to improve the representation of RSD in bulk microphysics parameterization schemes. So first, I'm going to talk about the ZR relation. So the question you might ask is, why do we want to use ZR relation to estimate rainfall? So here is a coverage of NextRad network. And now all these radars have been upgraded to dual pole radar. And we can see the coverage of the radar network is extensive. It covers almost the entire United States with very small gap. So if we have reliable ZR relations, then we're in good place to estimate rainfall for the entire United States. Then how we're going to develop the ZR relation using the observed RSD? First, let's look at how we calculate the Z and R. So the equation on the left calculates radar reflectivity, as we can see, is proportional to the sixth power diameter and the number concentration. And the rain rate on the right is proportional to the third power and the diameter and the total number concentration. And the RSD, that's the number concentration, that's where it goes in this equation. So for each sample that we collect, we can calculate a Z and R and plot them at a scatter plot and fit a line that's best using least square fitting, just fit a line there, then we get a relation, which is a power law relation with coefficient and exponent. And this figure is from Georgensen and Willis 1982. They used a similar data source, also the imaging probe from the hurricane flights. But unfortunately, the ZR relation varies significantly in different weather scenarios, and here I'll only list 3, but in the literature, there are easily over 100 ZR relations. Let's take a look at the ZR relation. So let's do that in our data sets. So this figure shows is a scatter plot. The horizontal axis is a log of rain rate, and the y-axis is a log of radar reflectivity. And the marker size is proportional to mass weighted diameter. You can consider that as drop size is a more complicated, but is related to drop size. And the color is denoted by the log of total number concentration. And we see quite a few interesting features here. So first, as we see, for a given radar reflectivity, as the rain rate goes up, the drop sizes decrease, and the total number concentration increase. This seems interesting, but actually, if you think about it, if you think about the equation that calculates Z and R, this kind of relationship is already implicitly included in that calculation. Let's take a look. So here we see the Z is proportional to sixth power diameter, and R is proportional to the third power. And so we consider a very simple case. We just have one size bin. If we reduce the drop size by half, in order to maintain the same radar reflectivity, the number concentration has to increase by a factor of 64. But for the rain rate, we have the number concentration increased by 64, but the size effect only reduced by 1/8. So in this situation, when the drop size reduced by half, the rain rate will increase almost by a factor of 8 if radar reflectivity remains the same. I said almost because the terminal velocity is also proportional to mass to the size, which complicates this situation a little bit, but really not too much. And another feature we noticed is as the radar reflectivity and rain rate goes up, the spectrum widens, and this indicates that precipitation is in a growing stage. And another more interesting feature is, as after 48 dBz, the drop sizes, the spectrum narrows. That's because the drop sizes are reaching equilibrium state. And the time for the drop sizes to reach equilibrium state decreases with the rain rate. That's why we see this interesting pattern in the scatter plot. And here we compare the ZR relation from this our data set with other studies, and the study that particularly close to our work is GW 1982 that the figure showed earlier. They also use imaging probes from hurricane flights. And I also put 2 ZR relation here. One is NWS tropical rainfall, the another one is NWS continental, just to give you a full picture. But also remember our ZR relation and the ZR relation from GW 1982 are from hurricane flights, not surface disdrometer. But very likely the NWS ZR relation are from surface disdrometer. So that's something we need to remember. But also remember from the previous scatter plot, when the dots are further to the right, then the size of dots are smaller, which means the drop sizes are smaller. So we can carry that information here, then we can tell basically from all these ZR relations, a tropical rainfall actually says, okay, the drop sizes are very small associated with this ZR relation. And also the 4 lines from GW 1982 give us some interesting information as well. If we look at this right line, that corresponds to the ZR relation from the eye wall, they are further to the right compared to the other 3 lines. So which tells us the drops are smaller in the eye wall. And then there are many other interesting features, but I don't really want to elaborate everything here. But basically, the table on the right lists all the estimated rainfall from the different ZR relations in the figure A for radar reflectivity ranging from 30 dBz to 50 dBz at a 5 dBz interval. What I want to emphasize here is like the numbers in these 2 right boxes. So when the radar reflectivity is 50 dBz, which is not very often observed in hurricanes, but they happen. And when the radar reflectivity is 50 dBz, the rainfall rate estimated from the JW 1982 composite is 74. But if we estimate from the tropical rainfall used by NWS, that's almost double what we get from the composite. So that says there are a lot of uncertainties. But we believe the information of drop sizes should be taken into account into the ZR relation to improve the rainfall estimates. And luckily, this mass-weighted diameter is proportional to differential radar reflectivity that can be measured by the WSR88D, the dual-pole radar now. And how we're going to improve the ZR relation? So we use a machine learning model, and the machine learning model I used here is a random forest regression, and the inputs for this model are radar reflectivity and mass-weighted diameter, as we see clearly from that scatter plot. And the output here is a perturbation, so is a log of the observed rain rate minus the log of rain rate estimated from the ZR relationship. So the figure we're seeing right now, the figure A on the left, is a scatter plot. The horizontal axis is the rain rate calculated from the observed RSD, and the y-axis is a rain rate estimated from the ZR relation. And we see actually it's pretty good. It has scatter, but we have to remember this is in log scale. And when I calculate the R square, it shows R square is 0.96. It's a pretty good number. But when I include that the perturbation from the forecast from the machine learning model, I'm able to increase the R square from 0.96 to 1. So which is a very good improvement. And now we're looking, these are in log scale, but in reality, when we talk about rainfall, we're not talking about rainfall in log scale. They're in linear scale. So in linear scale, this is what happens if we estimate rainfall from the ZR relation. We see the R square now is only 0.81, but when we add that perturbation, then the R square improves to 0.98, which is a significant improvement. And now, because I only have two features that feed into we feed into this machine learning model. So that's 2D. We can actually visualize the perturbation that in that 2D space. So this contour figure, the horizontal axis is radar reflectivity, and the y-axis is mass-weighted diameter. And the color is the perturbation that we see from the machine learning model. I have 2 color scales here, one corresponding to the relationship in log scale, and the color bar on the right is in a linear scale. So in the linear scale is more easily to interpret. So basically, this figure says whatever we estimate from the ZR relationship, we have to multiply by the number here, the right, the color bar on the right. So that's what we see here. So for small sizes, and we have to reduce the rainfall estimate, but for for small sizes, we have to increase the estimated rainfall that from the ZR relation. But for larger sizes, we have to reduce. And I also plot the data points that we have from the data set. And we see here, this is what our data lies in this space. And we see basically there is an envelope that encloses the data points. And then we see 3 regions, quite interesting. So A is top left corner, and B is bottom right, and C is top right. So top left corner, as we can see, it corresponds to very small reflectivity, but very large size, which is physically unrealistic. And B is similar, corresponds to very small diameter, very small size, but very large reflectivity, which is not realistic either. So, but C is something actually can happen in reality. It corresponds to large size and large radar reflectivity, but we don't see that in hurricanes. You might see that in severe continental convection, but we don't see that in hurricanes. So next, I'm going to talk about how we're going to use the observed RSD to improve the RSD representation in bulk schemes. So here, I'd like to give a little bit of background introduction about microphysics parameterization schemes. So overall, there are 3 levels of microphysics schemes, and their complexity increases dramatically from one level to another. So the simplest one is bulk microphysics scheme. It is very computationally efficient. The reason it is efficient is because it assumes the size distribution to be certain functions for all the hydrometers. And then we can have 1 moment, 2 moment, 3 moment. It really depends on how many moments these bulk schemes are forecasting. And the next level is spectral bin microphysics scheme. So they don't assume the size distribution. They actually resolve the size distribution by solving explicit microphysical equations. So in this case, how many equations really depend on how many bins and how many hydrometer categories. So if we're talking about 5 hydrometer categories and 40 bins, we're talking about 200 equations that bin scheme has to resolve, which is much more expensive than the bulk scheme. And the Lagrange particle-based schemes, and you can just justify by the name particle-based, which means this scheme, when if the resolution allows, they're actually resolving the individual raindrop and individual ice particle, which is, I mean, we cannot really use that for operation purpose for a long time. So for the operational purpose, so far we can only afford 1 moment scheme. So let's talk about, well, okay, you're talking about moments. What is moment? So moment is mathematical term. This is definition of moment. And the ND here is just any distribution. And we see like 0 moment, then n equal to 0, like 3rd moment and n equals to 3. So this is definition from Wikipedia. In mathematics, moments of function are quantitative measures related to the shape of the function's graph. But in microphysics, these moments actually are related, correspond to different microphysics variable. So when we talk about like when 0 moment, then we're talking about the number concentration. If the n equals 3, that's mass mixing ratio, and n equals 6, like we saw early, that's radar reflectivity. So then what is 1 moment scheme, 2 moment scheme? So for 1 moment scheme, they only predicts the max mixing ratio. And for 2 moments, they predict the number concentration and max mixing ratio. And for 3 moments, they predict all these 3. But for operational purpose, so far we can only afford 1 moment microphysics parameters, 1 moment scheme. So let's take a look what is inside this 1 moment scheme. So here because I'm only working with the rain data. So here the mixing ratio, that's the mixing ratio of rain, and that's a local tendency. On the right-hand side, we have 2 terms. And now I'm only interested in the terms in the right squares, because those are the terms where we can use the observed RSD. And the production term basically is just the summation of all the microphysical processes. And like probably over 90% of microphysics processes are related to the size distribution. Let's see how. So just take example at the RACW, that's rain accreting cloud water. So here we see this complete equation, but we see 2 parameters here. One is n naught, one is lambda. R here stands for rain. And now let's look at fallout terms. The fallout terms, the terminal velocity term is related to the slope. And this is from Lin scheme. So the Lin scheme also is used in the GFDL microphysics. Lin scheme only they assume the number concentration to be exponential form, and they fix the intercept, which is 0, and they diagnose the slope from the fixed intercept and the mixing ratio, which is prognostic variable for the scheme. But now look at the consequence of when we fixed N naught. When we fix N naught, if mixing ratio increases, then the slope has to decrease. When the slope decreases, it means we have larger increase in a larger drop number concentration, and this will lead to increase in radar reflectivity. And as we recall from a ZR relation, we see that the rainfall and radar reflectivity, they don't have the one-on-one relation. And when for the one rainfall, we can have different radar reflectivity values. So basically, this statement is often not true in the real world. Then let's see how we're going to improve the bulk physics scheme. So I show the two examples, the two samples. The histogram on the left actually looks very much like exponential, but the one on the right clearly cannot be represented by exponential distribution. So the function we use here is gamma distribution, and it has 3 parameters when the additional parameter is shape parameter compared to exponential distribution. So when the shape parameter equals 0, then this gamma distribution reduces to exponential. And then for each sample, we can fit a line here. Then using the gamma distribution to fit the observed sample, then we get 3 parameters because the intercept, shape parameter, and slope. So now we have over 18,000 samples, then we will have the over 18,000 of each parameter. And then we can use these 3 parameters to improve the scheme. So for the one moment bulk schemes, this is what we can do. So first, we can prescribe one parameter through a lookup table, which is not constant because it's from what we see from the observation, it cannot be a constant. Then we can calculate the second parameter from a relationship that is identified from the observation, and the third parameter can be diagnosed from the mixing ratio and the 2 parameters that we already got from the first 2 steps. But for the 2-moment scheme, which is actually, this is easier because we have 2 moments already, that if we have a relationship, then the gamma distribution can be fully determined. And now so before we do that, we have to fit the observed distribution, the observed raindrop distribution first using the gamma function. And the most straightforward way is to use least square fitting. But the experts from this field already demonstrated least square fitting does not perform well in this situation. The methodology people have been using for fitting the raindrop set distribution is called method of moments. And let's take a look at what they are. So here is a gamma distribution that we saw earlier. And here is a moments, and we also saw that earlier. And then by choosing 3 moments, we can have and plug in this gamma distribution to the moments. Then we have 3 equations. So this here I only show the example like 0 moment, 1 moment, and first moment and second moment, and we have 3 equations. And by solving the 3 equations, we can get the intercept, shape, and slope. So this is what I did using the 3 moments. But instead of using just 0, 1, 2, I want to toy with just different combination of moments. And I always choose 3 consecutive moments because then I always get a unique solution. When I choose like 0, 2, 4, I might get multiple solutions or no solutions at all. There might be some situations like that. So I always use 3 consecutive moments. So, and now I need to evaluate the performance of gamma fits. I have two aspects I'm concerned about. One is, does this gamma fit look like the observed distribution? And the second is, does the moments that calculate from the gamma fit agree with the moments that I calculate from the observed slide distribution? So first, look at the correlation coefficient, which measures how close the theta gamma distribution and look like the observed distribution. So the percentage on top of each column represents how many percentage in that samples that have correlation coefficient greater than 0.9. And we see this number actually decrease as the moments go up, like for M012, I have 76%, for M6, we have 23%. I only have 23%. But here's a deficiency when I use this M012. We see the mass width diameter, it does not perform well. And also the radar reflectivity is also severely underestimate the radar reflectivity. And for rain rate, it looks okay, but we have to remember these are plot, the radar reflectivity are plot at logs on the dBz scale. And so anyway, what I want for the feeding is I want the high correlation coefficient, and I want good agreement between the moments that calculate from the observed RSD and moments calculated from the fitted distribution. So what I did is I did a more holistic approach. I combined all the groups and extract the best fits from each group and compiled composite. So by doing this, I'm able to increase the percentage from 44% to 63%, also maintain a good agreement between the moments that are calculated from the observation and the fitted RSD. So next, I'm going to use this data, the 63% of this composite, to study the distribution of the three parameters. And each figure shows a scatter plot for each pair. So figure A shows the scatter plot between N0 and lambda, and figure B shows the scatter plot N0 and mu, and figure C shows the scatter plot of mu versus lambda versus mu. And for the a lot of papers, they actually identified some relationships either between or between lambda and mu. But from our result, we clearly see some trend, some relationship between these two, but the scatter is too big compared to what we see in this N0 lambda scatter plot. So in this N0 lambda scatter plot, I fit lines through the scatter points. I actually get like 0.92 this R squared that captures 92% variance. And the color is denoted by the log of liquid water content. So basically, we can see if we can include the information of liquid water content in this relationship, we might be able to get even better representation of this relationship. So this is what I did. I still use the machine learning model, the random forest. The input is a log of N0 and log of liquid water content, and the output is the lambda that's from the random forest. And so on the left, the scatter plot, the horizontal axis is lambda from we shouldn't really say from the observation, that's from gamma fits. And the y-axis is lambda that we calculated from that relationship. And we see, as we already see, that captures 92% variance. But when we use machine learning model to capture this relationship, we actually see a much better improvement. So here are my conclusions. For the ZR part, the part one, we see that large scatter in the ZR distribution imposes challenges on using the power law ZR relation to estimate rainfall. But if we take into account of mass weighted diameter, we can reduce uncertainties in the estimate rainfall significantly. And for the moment fitting and microphysics part, we see that if we use moments method moments that can produce bias when we feed the raindrop set distribution. But if we compile composite, we actually improve that the bias will be reduced, will be alleviated. And for the distribution, we identify a relationship that captures 92% variance for the N naught and lambda. And the remaining 8% can be further captured by including the impact of liquid water content. So from here, I'll take any questions.
Thank you, Hua. Excellent presentation. We have some time for questions. I don't see anything in the chat, so I'm going to open it up to the audience. If you have a question for Hua, please unmute yourself and ask your question.
Hi, Hua. This is John Gamache.
Hi, John.
So for each of these set of 3 moments, you solve to get the mu, lambda, and n naught, I guess.
Yes.
How do you combine? If you take from the different sets of moments, do you just average the values for?
No.
Parameters?
Okay, so that is actually a more complicated procedure, and it takes some time. So that's why I'll explain in the presentation. So because I have the lowest correlation coefficient percentage for the highest moments, like M456. So I start from M456. So in M456 group, I pick the samples that have correlation coefficient greater than 0.9, but also I noticed even for those samples, there are some bias when I calculate the lower moments, like number concentration. So I also set another threshold value that the moments, the number concentration difference between in the M456 group has to be less than 10. Then I move from higher moments to lower moments, but I use different variable for threshold value. So for higher moments, I'm 345, M456. I use total number concentration because that's where their weakness is. But for lower moments like M012 and M123, and I use I believe the mass weighted diameter because that's where their weakness is. So I just want to get rid of their weakness and extract the best.
Okay.
I'm not sure if
I'm realizing now that you actually compute that mu, the 3 parameters for each sample, and
yes,
and you're just showing a mode. But you show a mode in those figures. I don't know if you said that, but anyway, but that's just one possible value for those. So there is no one final mu, lambda, and naught that you come up with. It's just a distribution of them in which you see how it varies.
Yes,
is that right?
yes. So
yeah.
Because I think in the early, like I showed the Lin scheme, they actually fix N naught. I mean, so any distribution, the N naught is fixed. And from the observation, we know actually N naught varies by, so that's really not realistic. So, and also Lin scheme assumes exponential, and we know that exponential cannot represent all the distributions.
All right, so we have a couple of questions now in the chat. I'll read the first one that comes from Muchiko. Hi, Hua, very nice presentation. I'm curious about your random forest setups. How many data was used for training and testing, and how many trees were?
Actually, the random forest the algorithm is very easy to use. I actually tried different algorithm, like different random state, which corresponds to different split of the training data set and test data set. And then I see the difference really not that big. And when I use that for the test set, the performance is pretty good. So actually for here, what I show here is not from either the test set or training set. basically I use the entire data set as training set, but the results really does not differ much from if I just split that by like 70% or 30% or 80% or 20%.
Okay. So we have,
so
go ahead, Muchiko.
so sorry. Yeah. So you typically need to split that just to show that the result is valid. But I would take your word for that. I'm also curious about how many trees you built for random forest.
Oh, so the trees I used 100.
And how many data was it? How many pieces of data you used for training? Do you
About
remember?
10,000. About 10,000 data.
Okay.
Yeah, so over my overall data. Remember, I can only use about 63% of data. I cannot, like a ZR relation, I used all the data. But for the distribution, the parameter, the microphysics part, the gamma distribution, I cannot use all the data because some data we don't have good feeding. So I can only use 63% of data, and that about like over 10,000 data, over 10,000 samples. The overall, you can split that randomly into test set or a training set. Yes.
Right, thank you. I asked because your training feature is only 2, right?
Yes. Mm-hmm.
And then based on the random forest algorithm, it basically in my build fairly identical trees in your random forest scheme because your feature space is fairly small. But we can talk offline about the details.
Mm-hmm. Okay.
So we have another question from Trey. Nice talk. Did you say that only single moment schemes are computationally feasible for operational purposes, unless I misunderstood or misheard?
So far.
And are you talking about?
So far,
Well, let me finish the question. And are you talking about bin, bulk, or both? And what about Thompson?
Okay, Thompson is like a semi two moment. I say semi two moment is because it does not have two moments for all the hydrometer categories. I think it has two moments for cloud water. I'm not sure about cloud ice, but Thompson, my personal experience with Thompson is when I run Thompson, it consumes like 25% more time than Lin scheme. And when I talk to people from EMC, and their impression is they're even struggling with the GFDL, which is like one moment. They're even struggling at time-wise. They're even struggling with that. So for the operational purpose, I don't think we're going to use 2 moment, let alone 3 moment. The bin scheme is completely out of the question because they're just way too expensive.
Okay, so I have a follow-up from John Gamache. How would cloud physics parameterizations use your 3 moments? If they use such a scheme, would they use your mode? Maybe this is too complicated to address here.
No, the 3 moment scheme, actually, if you look at a 3 moment scheme, they don't need anything from the observation because they already have 3 moments. They can just solve the 3 parameters based on the 3 moments. Because when we talk about 3 moments, we think 3 moments are 3 equations. Then we just, if we have 3 equations, we can solve for 3 unknown variables. So,
yeah,
but
go ahead.
Mm-hmm.
No, what I was going to ask is, so how do you envision the microphysics scheme, say like the Lin scheme or GFDL scheme that you're talking about? How would they use this information? Would they use a lookup table? Do they have dependent variables that would be used?
Okay, so what I'm working on right now is because GFDL is 1 moment scheme. In order to improve the 1 moment scheme, we need to provide 2 pieces of information. One, we need to give them like ways to predefine 2 parameters because they can only diagnose 1 based on the mixing ratio. So like I mentioned in the slide, that for 1 moment scheme, we have to provide them a lookup table. The lookup table will be calculated based on the environmental variables such as the temperature, the mixing ratio, the relative humidity, and maybe the wind speeds. That's something I'm working on right now. And if we have the lookup table, then now we have this relationship that's identified from the data set. So then we can calculate the second parameter based on the relationship and the lookup table. Now we have 2 parameters. And then the third parameter can be just diagnosed from the mixing ratio.
Right. So the only variable really coming from the model is the mixing ratio. Is that what you're saying?
Yes, for one moment.
Okay. Any other questions? There's a couple of comments,
Yeah.
but I don't see any other questions. Any other questions? Okay, I don't hear any other questions. I don't see any other questions on the chat. So I want to thank you, Hua, for an excellent talk. I'm looking forward to seeing how you apply this approach to the microphysics schemes. And with that, we'll end the seminar today. And thank you, everyone, for your attention.
Okay, thank you.